All right, let's do another example of finding Taylor polynomials. This is another function, sine x, and I'd like to find the Taylor polynomial for sine x at x equals 0. So here's my answer. The Taylor polynomial looks like a0 plus a1 x minus a. In this case, I'm taking a to be 0, so x minus 0 to the first, plus a2 x minus 0 squared, and so on. So I keep going until I get a big term over here, the nth degree maybe. All right, so we found that the kth coefficient in my Taylor polynomial is the kth derivative of my function evaluated at a, in this case a is 0, divided by k factorial. The function sine x. So I'm going to take a bunch of derivatives of sine x, find a pattern, and use it to determine the kth coefficient in my polynomial. The derivative of sine x, cosine x. Derivative of cosine x, negative sine x. Derivative of negative sine x, negative cosine x. The fourth derivative of my function is sine x. And I'm back where I started. So the fifth derivative is going to be the same as the first derivative. This pattern is going to continue. So the derivatives are always going to be sine, cosine, negative cosine, and then repeat. So what happens if I plug in x equals 0? I'd like to get these values. So sine of 0, 0. Cosine of 0 is 1. Negative sine 0 is 0. Negative cosine 0 is negative 1. Sine is 0, 1. And this pattern will continue as well. The numbers will be 0, 1, 0, negative 1. 0, 1, 0, negative. Repeat forever. So that gives me my Taylor polynomial. My function y is the 0th derivative, which is 0, divided by 0 factorial x to the 0. X to the 0 is 1. I kind of just put it in so it matched the other terms, but that's the first term. It's just 0. The next term, 1 over 1 factorial x to the first. The second term, 0 over 2 factorial x squared. Then I'm going to get negative 1 over 3 factorial x to the third, plus 0 over 4 factorial x to the fourth, plus 1 over 5 factorial x to the fifth. And then I could keep going. So the coefficients 0, 1, 0, negative 1 are what I'm writing down here. 0, 1, 0, negative 1. 0, 1, 0, negative 1. Okay, so that's an answer, but I'd like to write it a little bit simpler. I don't need to write down all the terms that are 0. If you'll notice, only the odd exponents have a non-zero coefficient. So I'll just write those down. I have x minus 1 over 3 factorial x to the third, plus 1 over 5 factorial x to the fifth, minus 1 over 7 factorial x to the seventh, and this keeps going. So that's a good answer. That's a perfectly nice answer. but it's kind of long to write out. So to abbreviate, I'm going to use sigma notation, meaning just add up all this stuff. So I'm going to go k starting at 0 and maybe going up to n. So I'm going to add up the terms starting from k equals 0 to n. Now, I'm going to take the kth term to be an odd number. An odd number is something of the form 2k plus 1. If I plug in a value for k, 2k plus 1 will always be odd. So if I take k equals 0, I get 1 factorial. If I take k equals 1, I get 3 factorial. If I take k equals 2, I get 5 factorial. So I'm getting only the odd terms you see here. The power of x that goes along with this term is x to the 2k plus 1. I see like 7 here is the same as the 7 here, so those match. Now, if you also notice, I have alternating terms. So the terms switch from positive to negative, positive, negative, positive, negative, positive, negative. To get that in the sum, I'm going to take minus 1 to the k power. You could see that this term will make the flip-flopping signs. So if k is 0, I get negative 1 to the 0, which is 1. If k is 2, or excuse me, if k is 1, I get a negative. So this is the formula for the Taylor polynomial for sine x at x equals 0. This is actually a pretty important example. This is actually the degree. If I plug in k equals n, I think it'll be the degree 2n plus 1 Taylor polynomial for sine x. Okay, great.